Hello and welcome all of you to this lecture session of Heat Power Engineering. In the previous lecture sessions, we have understood the concepts of first law of thermodynamics, which is applied to both open and closed systems, and then we had gone through an intense session on the second law of thermodynamics. So today we will be solving some numerical problems regarding the first law and the second law of thermodynamics, so that our concepts about these two fundamental laws can be understood very well. So let us start with our first problem. So if you go through the problem, a slow chemical reaction takes place in a fluid at the constant pressure of 0.1 megapascal. So here you can see that it is a constant pressure. The fluid is surrounded by perfect insulator during the reaction, which begins at state 1 and ends at state 2. So this is the first process 1 to 2. Okay, so during process 1 to 2, you can say that the there is a perfect insulator present, and here you can obviously understand if there is an insulator present, then there will be no heat transfer. So it is quite obvious that during the process 1 to 2, heat transfer is 0. So it is very easy to understand that the heat transfer during the process 1 to 2 is 0. Now the insulation is then removed and 105 kilojoule of heat flows to the surroundings as the fluid goes to the state 3. So now if you concentrate on the process, 2 to 3, then what happens? 105 kilojoule of heat flows to the surroundings. So heat is flowing from the system to the surroundings. That means it is obviously negative heat transfer. So we can write dq for process 2 to 3 as minus 105 kilojoule. Okay, I think it is very well understood now. Now during these two processes, during the process 1 to 2 and process 2 to 3, the pressure is remaining constant. So that has been mentioned in the first line of the problem. Okay, so it is being also mentioned. P constant is, and what is the value of this constant pressure? It is 0.1 megapascal. Okay, so it is easy to understand now. Now here you can see the following data are observed for the fluid at states 1, 2 and 3. So for the states 1, the volume is given 0.003 meter cube. The state point 2 refers to 0.3 meter cube, and for the state point 3 it is 0.006 meter cube. The temperatures corresponding to the three states are also mentioned here. Now the question is you need to find out the change of internal energy. So I have missed out the question. You need to calculate the internal energy at state point 2 and state point 3 when U1 is 0. Okay, so when U1 is 0. So this is a question. You need to calculate the internal energy at state point 2 and state point 3 when the internal energy at state point 1 is 0. So this is a very simple application of the first law of thermodynamics. It is very easy to understand. Now writing the first law of thermodynamics for the process 1 to 2. So it is dE 1 to 2. dE means the change of internal energy plus dW 1 to 2. Okay. Now you can understand that dE 1 to 2 means E2 minus E1, right? And now E1 is already given as 0, so there is no need to write this. We can see that E1 is 0, E1 is 0, so there is no need to write this. We can simply write E2 plus dW2, sorry, dW1 to 2. That means the work transferred during the process 1 to 2. And here dQ1 to 2 has been 0 because the fluid was insulated during the reaction which started at state 1 and ended at state 2. So this is also 0. So we can write 0 here. So 0 is equal to E2 plus dW for process 1 to 2. Then it is quite obvious, it is very easy to understand. Then E2 will be, that means the internal energy at the state point 2 will be minus of dW1 to 2. Now our question is, how can we find this work transfer during the process 1 to 2? So during the work transfer, you can observe that the pressure had remained constant. There is a change in the volume. Okay, so when pressure remains constant and there is a change in volume, then the work transfer can be simply calculated by the basic formula. You know the formula of displacement work. It is integration of PdV. It is integration of PdV. So as it is known to us and the state points are 1 to 2, that means we'll later on write down the volume state points. So we can write this P is remaining constant, PC, from state point 1 to state point 2. So integration of dV. Now you know what the integration of dV is. So it will be PC into V2 minus V1. Very simple thing to do. Now you have the value of this Vc. It is 0.1 megapascal. It is 0.1 megapascal. Okay, and the change in volume is 0.3 minus 0.003. Okay, so if you do the relevant calculations, you will find the work done during the process 1 to 2. You will find that the calculation yields the value of 29.7 kilojoule. Okay, so it is very easy to calculate. Now if you put the value of this work done, which is done for the process 1 to 2, then it will be minus 29.7 kilojoule. Okay, it is very easy to understand now, I believe. So it will be minus 29.7 kilojoule. Okay, now coming on to the next part where we need to calculate the internal energy at state point 3. Again, we would be applying the first law of thermodynamics, but now for a different process. So it is dq for process 2 to 3, which is equal to dE for process 2 to 3 plus dW 2 to 3. So we have already found out the heat transfer for the process 2 to 3, and it was minus 105 kilojoule, because when the insulation was removed, 105 kilojoule of heat flowed to the surroundings. So we can write this is 105 minus 105, and we can write the change of internal energy for the process 2 to 3 as E3 minus E2. Okay, very easy to understand. Plus dW 2 to 3. Now again, we would be requiring to calculate the work done during the process 2 to 3, and we must understand for the process 2 to 3 the pressure had again remained constant. the pressure was kept constant, and the constant pressure being 0.1 megapascal. So it remains exactly as it was earlier. But the state points, the volume had changed. So we must acknowledge the volume because the states have been changed. So 2 to 3 for the process. So the work done for the process 2 to 3 can be calculated by the simple integration, where the volume changes from state point 2 to state point 3, and here we can write V3 minus V2. Okay, V3 minus V2, and here V3 has been given as 0.006 minus of 0.3, and the pressure is still 0.1 megapascal. Now you need to do a simple calculation. So after doing the calculations, you will find the work done is minus 29.4 kilojoule. So now you have the work done for the process 2 to 3, and you can simply put that value. You know what is the value of E2 because you have already calculated it. So it will be plus 29.7. So it will be plus 29.7, and it will be minus 29.4. Okay, so therefore E3 can be calculated as minus 105.3 kilojoule. Okay, so therefore we can calculate the internal energy at the state point 3 and the state point 2. Okay, so this is a very simple application of the first law of thermodynamics and the work done. Okay, so this is a displacement work formula. We have already taken some numericals regarding this. So if you are able to understand the work done during this constant pressure process, then it is a very simple problem. Okay, so with this, let us move on to the next problem and see how it is. Okay, so you can see that 1.5 kg of a fluid having a constant specific heat of 2.5 kilojoule per kg Kelvin is stirred in a well-insulated chamber, causing the temperature to rise by 15 degrees Celsius. Find delta E and W for the process. So what is happening in this process? It is a insulated chamber. That means there is no heat transfer from the outside. Okay, so the stirring is going inside, which is increasing the intermolecular energy. Okay, so you can say that the mass of the fluid is equal to 1.5 kilojoule. 1.5 kilojoule. I'm sorry, this is 1.5 kg. Very sorry. Okay, so the specific heat is 2.5 kilojoule per kg Kelvin. Kilojoule per kg Kelvin. Okay, very easy to understand. And what is the rise in temperature? You can write delta T. The rise in temperature is 15 degree Celsius, or you can write as 288 Kelvin. Okay, so you can write this one as 288 Kelvin. Okay, so 288 Kelvin it is. Now the question is, it is well understood, I believe, that there is no heat transfer here because the chamber is insulated, so no heat transfer is possible from the outside. So this dq would become 0. Now writing down the first law of thermodynamics. So this is a very easy problem, I must say. So it will be a dE plus dW. dE plus dW. Now the question is how we can find this dE. Very simple thing. The intermolecular energy is getting increased because of the stirring action. Okay, so since the intermolecular energy is increased, we can write this dE as m mass into the specific heat into the increase in temperature. So we can write 1.5 multiplied by 2.5, and we can write that it is 2 into Kelvin. So this is the change in internal energy, or this is the increase in internal energy because of the stirring action which is caused by the stirrer. So now if you do the relevant calculations, you will find that D becomes 180 kilojoule. Now dQ is 0. That means dW will be equal to minus dE. Okay, so dW will be minus of dE. That means minus 1080 kilojoule. That means 180 kilojoule of work is done by the surroundings on this system. Okay, so thus we can calculate this problem. So this was a very easy problem. Okay, so with this, let us move on to the third problem, where we can see the second law of thermodynamics we applied. Okay, so just read out the problem here. A domestic food freezer maintains a temperature of minus 15 degrees Celsius. The ambient temperature is 30 degrees Celsius. If heat leaks into the freezer at the continuous rate of 1.75 kilojoule per second, what is the least power necessary to pump this heat out continuously? So before doing this problem, we must understand the working principle of the refrigerator. So refrigerator is a device which maintains the cold place cold. Okay. Now a domestic food freezer maintains a temperature of minus 15 degrees Celsius. That means the objective of this freezer is to maintain the temperature of minus 15 degrees Celsius. Now what is the restriction? Why isn't this refrigerator able to maintain the temperature at minus 15 degrees Celsius? Because the ambient temperature is 30 degrees. That means you know that if the ambient temperature is higher than the place which is maintained at minus 15 degrees Celsius, then what will happen? Heat will be transferred from the high temperature to the lower temperature. That means there will be constantly heat transfer from the ambient to the freezer space. So that means refrigerator should always reject this heat which is coming from the ambient. So refrigerator must do something to transfer this heat out continuously, so that the cold space remains at minus 15 degrees Celsius. Okay, now the question is, what is the least power necessary? Now you must understand, you must know that reversible process gives the maximum efficiency, or the reversible heat engine gives you the maximum work. Reversible heat pump or reversible refrigerator consumes the least work. So this is very simple to understand. Reversible process gives you the maximum efficiency. Now what happens? Heat engine produces work, so it will produce the maximum work, and heat pump and refrigerator, they consume work, so they will consume the minimum work or the least work to give the maximum output. That means it will be able to maintain the cold space at minus 15 degrees Celsius. So now the question is, so we have already defined the temperatures. Now heat leaks into the freezer at the continuous rate of 1.75 kilojoule per second. So now the question is, you need to find out this W, which is the least power, when this Q2 is given as 1.75 kilojoule per second, because the refrigerator needs to pump this amount of heat continuously, so that this cold space can be maintained at minus 15 degrees Celsius or 250 Kelvin. Okay, now this is a very simple problem. Now if you have the value of Q2 with you, then for a reversible process, you can simply use this formula. Q1 by T1 is equal to Q2 by T2, or in other words you can say Q1 by Q2 is equal to T1 by T2. Now what is the value of Q1? That is the unknown thing. Okay, so why you are calculating this Q1? That must be answered, because W is equal to Q1 minus Q2. We have the value of Q2, but we don't have the value of Q1. So Q1 needs to be calculated. So Q1 by 303 is equal to 1.75. It is kilojoule per second, or we can write kilowatt. So joule per second is watt, so it will be 1.75 kilowatt by T2, or we can write 258. So if you do the calculations, you can find the value of Q1, and it will be, so you will find Q1 as 2.06 kilowatt. Okay, so you can find this value. Now the question is to calculate the least power. So remember why we are able to use this formula, because in the question it has been asked to find the least power, and to find the least power we must understand that the process should be reversible. Okay, so this is a very important concept you must understand. So W is equal to Q1 minus Q2, so it will be 2.06 minus 1.75. okay, that will give 0.31 kilowatt. So this is the least power necessary to pump the heat which is coming from the surroundings or the ambient continuously. So with this we can end this problem here. So this was a very conceptual problem. You must understand, to give the maximum efficiency you should always go for a reversible process. And when we are considering a refrigerator which is in operation, its reversibility means that it will consume the minimum work so that it can maintain the space at this specified temperature. Okay, so with this we can end this problem, and we can move on to the next problem. So this is the last problem here for this session. So let us see the problem statement. A heat engine is used to drive a heat pump. The heat transfers from the heat engine and the heat pump are used to heat the water circulating through the radiators of a building. The efficiency of the heat engine is 27% and the COP of the heat pump is 4. Evaluate the heat transfer to the circulating water to the heat engine. Okay, now the question is, a heat engine is used to drive a heat pump. So let me draw the figure for you. Okay, so here you can see this diagram. This is not up to scale though. So there is a heat engine which is receiving heat from a source which is maintained at a certain temperature. Since it is not given in the problem, we need not bother about the temperature here. And this is the sink. Okay, similarly, so the heat engine is operating between the source and the sink, receiving heat Q1 from the heat engine and rejecting heat Q2. So this Q2 is a heat transfer from the heat engine. Okay, very easy to understand. Q2 is the heat transfer from the heat engine, not Q1, because Q1 is a heat transfer from the source. Similarly, this is your sink over here for the heat pump, and this is the source. Obviously, they both of this source and sink, they are maintained in different temperatures for heat engine and the heat pump. The question is, this heat pump receives Q3 amount of heat from the sink, whereas it delivers Q4 amount of heat. So the heat transfer from the heat engine is Q2. Q2 is the heat transfer from the heat engine, whereas Q4 is the heat transfer from the heat pump. So the question is, you need to find out the heat transferred to the circulating water to the heat engine. Now here this is the question, and the heat transfers from the heat engine and the heat pump are used to heat the water circulating through the radiators of a building. So it is obvious that it will be Q2 plus Q4 divided by the Q1. So heat transfer to the circulating water means heat transfer from the heat engine, that is Q2, heat transfer from the heat pump, that is Q4. So the total heat transfer to the circulating water is Q2 plus Q4, and the heat transfer to the heat engine. So Q1 is the heat transferred from the source to the heat engine. So it will be Q2 plus Q4 by Q1. So now we need to calculate this Q2 plus Q4 in terms of Q1. Now how we can do this? This is a very simple thing. Okay, so let us start our problem. Now initially it has been given that the efficiency of the heat engine is 27%. So eta heat engine is 27 by 100. That can be simply written down, 27 by 100. Now what does the efficiency mean? It means that 1 minus Q2 by Q1 is your efficiency. Okay, so 27 by 100. And now you can easily see that Q2 by Q1 will be 73 by 100. So Q2 can be written as 0.73 Q1. So Q2 can be written as 0.73 Q1. Now coming to the COP part, COP of the heat pump is given as 4. COP is given as 4. Now what is this COP? This COP is nothing but the heat which is being delivered at the high temperature, that is Q4 here, and it is the work input. Corresponding to the work input, Q4 heat is being delivered. So you can write 4 over here. Okay, so Q4 by W is equal to 4. Now if you do the simple calculation, Q1 minus Q2 is your W. So for the heat engine, Q1 is equal to W plus Q2, doing simple energy balance, and you can say that Q1 minus Q2 will be equal to W. Now what is this Q2? 0.73 Q1. So you can very easily write that W is Q1 minus 0.73 Q1. So it will be simply 0.27 Q1. Okay, very easy to understand this thing. So Q4 would be 4 into 0.27 Q. I am replacing this by this value which we have just now obtained. So 0.27 Q1. So Q4 would be 1.0808 Q1. So we have this Q2 in terms of Q1 and we have this Q4 in terms of Q1. Now I'll be just removing all these calculations which we have done till now, because we only need these two data here. So you can see now that we have Q2 is equal to 0.73 Q1. So it is 0.73 plus 1.08 Q1 divided by Q1. Q1 divided by Q1. Okay, so it will be simply 1.81 Q. Okay, sorry, this Q1 will be removed. So the ratio of the heat which is being transferred to the circulating water to the heat transferred to the heat engine is nothing but 1.81. So I believe now you have understood how this problem can be solved. So you must understand what is the heat transfer from the heat engine. So from the heat engine, this Q2 is the heat transfer. From the source, the heat Q1 is transferred to the heat engine. Now heat engine transfers this Q2 heat to the sink. HP, this heat pump, takes heat Q3 from the sink. So sink transfers Q3 heat to the heat pump, and heat pump transfers Q4 heat to the source. So if it is understood well, then the problem becomes a very simple one. So with this, we will complete our session today. In the next lecture session, we will start a different module. So till then, goodbye and thank you all.